Today we'll be exploring the fundamental principle of mechanics, Newton's second law, which states that the force exerted on an object is equal to the object's mass and acceleration. Based on this principle, other formulas can be derived, which can be used to help describe the motion that we see in our everyday lives. The experiment I conducted today videos, tracks, and plots the motion of an object, in my case a soccer ball, at a constant velocity. First, I will use Newton's second law to explain the motion of the object. Afterwards, I will compare the distance versus time plot of the object in the video to that of a computational model of the object created using predicted motions in VIDLe. Here is the video of the soccer ball a few seconds after it has been kicked. The ball's point of mass is identified at each frame, which thus helps trackers chart the ball's change in position. It should be noted off the bat that the point mass is identified through my own estimation, and the ball does not move in a straight line across the street. Given that the object is moving at a constant velocity, the acceleration on the object, which is equal to the object's change in velocity, Vf minus Vi, is 0. Thus, the net force, according to Newton's second, is also 0. Subsequently, it could be predicted that the distance versus time graph of the object will follow a linear trend. A computational model of the object is then created using VIDLe. The model creates a plot based on the predicted movement. Now, these predictions are created by setting the initial conditions in the program and using equations derived from Newton's second law. Now, some initial conditions would include the ball's mass, the ball's initial position, the ball's initial velocity, as well as, most importantly, the ball's net force, which we said earlier because the velocity is constant, the acceleration would be 0, thus the net force would also be 0. Now, these are the equations derived from Newton's second law that inputs the values from the initial conditions and outputs the new predicted movement. For Newton's second, all we need is the initial position and the initial velocity to make predictions about the translational movement of the object. Now, we start by inputting the ball's initial velocity onto this line such that we can be able to compute the ball's final velocity. Now, once we input the ball's initial velocity, we know that the net force for this object is going to be 0, given that it's traveling at a constant velocity. And so, just based off on this, we know that the ball's initial velocity is always going to be equal to the ball's final velocity. Now, once we have this computed, the ball's final velocity can thus be input into this line and multiplied by the change in time and added to the ball's initial position. And all of this would equal to the ball's final position. And the t equals t delta t would essentially facilitate the time steps. So once you have a final time, it'll be input back into the first line of equation and to find the ball's new final velocity. And so this process repeats itself again and again in time steps, which essentially forms an iteration. Now, these predictions that construct the prediction line for the graph isn't made all at once, but rather so it's made from one small time step at a time using these iterations. Okay, so now that we have our two plots, one created by the computer module using VIDLe and the other created using Tracker, we can now put the two graphs side by side and see how they compare. Okay, so I compared these two graphs by plotting the data points on using Google Spreadsheets and then putting them onto one graph. And as we can see here, the red line denotes the position versus time of the computational model, and the blue dots represent that of the actual video. So as we can see, the computational model actually overpredicts the position of the ball. So we can see this for a number of reasons. For starters, the values that I used to calculate the initial velocity for the computational model were simply from the first and second time frame. That means that had we used the first and the last time frame, maybe the velocity would have been a little bit more accurate. Another reason is that while the ball was rolling, it did not stay in a straight line, rather it drifted up and down, which again skewed the position. Finally, the computational model can now take into consideration forces acting on the system from its surroundings, such as air resistance and friction, which affect its motion. Now, if we were to flip the axes of this graph, such as this is the negative x direction and this is the positive, the ball will roll in an increasingly negative direction, thus the constant velocity and the slope of the graph would be negative. Now, the computational model generally worked well in predicting the ball's motion because the net force is equal to 0. The net force is 0 because the total pushes and pulls that add together on the object is equal to 0. The diagram shows the forces acting on the ball as it rolls. Because the ball is not moving in the y direction, we know that the total net forces in the y component is equal to 0. In regards to the x direction, however, there are three forces on the ball: the initial kick that started its motion, air resistance, and friction. Because air resistance and friction are so small in this observation, their values are negligible. The force of the kick that set the ball in motion, however, is not easily quantifiable. We know that the total force has to equal 0, thus the force of the initial kick is also equal to 0. Now, if you're asking yourself how the ball continues to move even when the force of the kick is 0, keep in mind that while the ball does not have a net force, it does have a momentum, which is calculated by multiplying the mass and the velocity. Now, with that, I conclude my report for the day. Hope you've gained a clear understanding of the application of Newton's second law as the foundation of mechanics.